All right, this is section 24.4, obtaining the value of the electric field from the electric potential. Let me dismiss my image. And we have here a uniform electric field produced by an infinite sheet of charge. And you can see that these blue, this is the field, the arrows are the electric field, and the blue lines are the equipotential surfaces. So delta V is equal to minus the integral from A to B of E dot ds. dV is equal to minus E dot ds, and E dot ds is equal to EDX, EX dx. We're talking about in the X direction. So E to the X is equal to the minus dV dx. So basically the X component of the electric field is equal to the negative of the derivative of the electric potential with respect to X. Okay, so here we have a spherically symmetric electric field produced by a point charge. And you can see here's the point charge. You can see the electric field lines going out radially, and you can see the equipotential surfaces surround it. Now here's an electric field produced by an electric dipole. You have the positive, you have the negative. The electric field is emanating from the positive and going into the negative. And you can see that the the equipotential surfaces are follow uh, the field lines, and that at every point they're perpendicular. Um, so E dot ds is equal to ER dr, dV is equal to minus ER dr, and ER is equal to minus dV dr. It's similar to what we had. EX is equal to minus dV dx. So the we have the EX is equal to the negative, the partial of V with respect to the partial of X. EY is equal to the negative of the partial of V with respect to Y, and EZ is equal to negative of the partial of V with respect to uh, Z. And let's see, I've got it's ordinarily this uh, you know, in more advanced courses, you'll see this as the del. It looks like an upside down delta. Minus del V is equal to uh, the negative of I partial with respect to X plus J, partial with respect to Y plus K, partial with respect to Z, and of V. So that's in your footnotes on section 24.4. They don't give you a graphic here. Okay, in a certain region of space, the electric potential is zero everywhere along the x-axis. From this information, you can conclude that the x component of the electric field in this region is zero. Why? Because it's constant. I mean, it's a constant, and so it's zero. Now, suppose the electric potential is plus two volts everywhere along the x-axis. From this information, you can conclude that the x component of the electric field in this region is zero again, because it's a constant, and the derivative of a constant is equal to zero. And that's the end of section 24.4.